Welcome back to the workshop. We want to continue taking a look at section 3.4 on probability density functions, and we want to take a look at a couple of theorems regarding them. The first one is rather intuitive. The second one matches very closely with a theorem from section 3.2, so you should be able to compare with that, but we'll also take a look at an example. So let's take a look at our notes. So if we have a continuous random variable x, and a and b are real constants, real numbers with a less than or equal to b, then the probability that the random variable takes on the values between a and b, right? This is our typical notation. But this is in fact equal to the probability that it's strictly greater than a, or less than or equal to b, or the same as a less than or equal to the random variable strictly less than b, or saying that it can't take on either one of those particular values, a or b. So we can add or drop the equality as we want to, and it will actually keep the same value. But of course, that makes sense because for any function that's defined at a, the integral from a to a is exactly 0. So we can express these right without this. Adding or subtracting this particular value does nothing at all. So that should make sense for us. And then a theorem similar to what we saw in section 3.2, what kind of functions can serve as probability density functions? Well, it can serve as long as two conditions are satisfied. The first being that the function values are greater than or equal to 0 for x values between negative infinity and positive infinity. So it's non-negative, all right? Now, this actually is not required for those that take a measure theory course, sometimes called a real analysis class, not Math 441 of an undergraduate class, right? Not Math 441 here at CUAA, but rather a real analysis for a first-year graduate level, or maybe really an upper level at a institution that might take them a little bit further for undergraduates. But nothing you'll see here. But if you take a measure theory class, they'll talk about how you can have a countable number of points that don't agree with what you'd really like, and it actually doesn't cause any problems. So if we wanted to, we could actually have a countable number of places where the function is negative, and that would be okay for a probability density function. So this could be changed to an if and only if statement if we could somehow make that statement that taking on negative values is actually okay sometimes. But since it's difficult to express that and unnecessary here, we'll just simply say if it's going to satisfy these two, then we know it can be a probability density function. And we'll just leave it at that for now. Okay, so the first thing is non-negative. Easy to say, easy to check. All right, the other thing is that the integral from negative infinity to positive infinity over all possible values of the random variable, f of x dx is equal to 1, right? Essentially the probability of the sample space is exactly 1. That's what we want to find there. All right, so let's check and see whether this function can serve as a probability density function for some continuous random variable. All right, and all that requires is referring back to the previous theorem and saying, all right, is it non-negative, and does the integral equal 1? Okay, and I chose an awesome function here that is actually defined for all real numbers. So it's non-zero, and we actually have to integrate over the entire real line. If you wanted another example, if you wanted to confirm, what I would encourage you to do is I would encourage you to check this function, make sure that it is non-negative everywhere, and make sure that the integral over the entire real line is in fact 1. And you should find that both of those conditions are satisfied. So I'd encourage you to check this out if you need another example. But for us to help with a little bit of recall on integration techniques, we're going to go ahead and take a look at this particular function. So the first condition that we need to satisfy is that it's non-negative. And that should be pretty obvious, but let's make a couple of statements. First of all, any number squared is greater than or equal to 0. Excellent. So when we add 1 to that, we're going to get that x squared plus 1 is strictly greater than 0. And then if we were to take 1 and divide it by something that's strictly greater than 0, we should still get something that's greater than 0, so that if we add a factor of pi to that, we still get something that is greater than 0. Awesome. So we have the first condition is satisfied. The next thing that we need to check is that the integral over the entire real line is in fact equal to 1. So let's see here. We need that the integral from negative infinity to positive infinity of the function itself is equal to 1. So we want to find that. Well, what is our function in this case? Well, our function is 1 over pi times x squared plus 1. So to evaluate a improper integral, this is called, right? We don't have division by 0 anywhere, so there's no concerns about that. We don't have any vertical asymptotes to worry about, but we can't take, we can't actually evaluate at positive and negative infinity. We have to use limits here. And we also cannot do two limits at the same time on one thing. So we have to separate it and then apply limits to both of those pieces. So we're first going to separate it, call it 1 over pi times the integral from negative infinity to 0 of 1 over x squared plus 1 dx, plus the integral, or 1 over pi times the integral from 0 to positive infinity of 1 over x squared plus 1 dx. Awesome. So that's the first thing we have to do. Once we're here, we can integrate and evaluate and use limits in that evaluation. Now, this actually works out to be one of the integrals that's typically given in a cheat sheet. So awesome. You could also use trigonometric substitution to evaluate these, but you should be able to recognize pretty quickly that what you're getting is, first of all, use limits. So let's let a go to infinity. The integral should be the arctangent function. So this is arctangent of x evaluated from a to 0, and we're letting a go to negative infinity. And then this is plus 1 over pi times the limit as b goes to positive infinity. The integral is still arctangent. And we're evaluating from 0 to b, letting b go to infinity. All right, when I evaluate, it's the evaluation here minus the evaluation there, evaluation here minus evaluation there. So what I'm going to have is that this is 1 over pi times the arctangent of 0 minus a, get rid of that for now, and then b minus 0. So arctangent 0 minus arctangent 0. Of course, those two cancel out. It's nothing. Plus, I've got the limit as b goes to infinity right here, arctangent b. So this is plus the limit as b goes to infinity. Oh, and actually, let's add a 1 over pi to this. Limit as b goes to infinity of the arctangent of b. And then we have minus, right? Arctan evaluated at 0 minus arctan evaluated at a. So minus the limit as a goes to negative infinity of the arctangent of a. Excellent. So these two things over here cancel out. Bam, bam, they're gone. They're actually both 0 anyway, but that doesn't matter because they're the same thing. 1 minus itself, or the thing minus itself goes away. So we still have 1 over pi, and then the limit as b goes to infinity of arctangent is pi over 2. So pi over 2. And the limit as a goes to negative infinity of the arctangent of a is negative pi over 2. So minus negative pi over 2. And what we're left with is 1 over pi times pi over 2 plus pi over 2 is pi. Pi's cancel out to leave us with just 1. Yes! Excellent. So the integral over the entire real line is in fact just 1. So can this function serve as a probability density function for some continuous random variable? Thumbs up. Yes, it can. And that's all that we wanted to show. So for now, we'll stop here and we'll pick back up with another definition and another example in our next video. So I'll see you guys back in the workshop very shortly.